indicated by this term. Okay, I think the recording just started. Okay, all right. So this becomes then the optimization problem. We're maximizing social welfare subject to a budget constraint on the amount of treatments we can provide, and subject to a constraint that defines the level of utility right here. Okay, so again, the goal here is to try to give some guidance for how to incorporate an equity-sensitive objective function into an existing optimization model. All right, so I'm going to begin with inequality measures. The simplest, perhaps most straightforward way of measuring equity. Do people get the same thing? The problem is that equality is not the same thing as fairness. It's related somehow. And if you look at the philosophical literature, there's absolutely no consensus on the relationship between these two. So there's one school of thought that equality is desirable in and of itself for its own sake. And there's also the opposite school of thought, is that the inequality is bad only to the extent that it reduces total utility. So as you may know, inequality has negative effects. You have social unrest and so forth, and dissatisfaction. Is that the only reason it's bad? Well, there's no consensus on that. So that's a problem in formulating it. There's lots of ways to formulate inequality, but we don't know which one to use for this basic reason. Another problem with just measuring inequality is it doesn't take into account how well off people are in general. Okay. Also, a problem if you're just measuring inequality, it counts inequality at the top of the distribution just as much as at the bottom, whereas perhaps we should be more concerned about people on the bottom. So these are some weaknesses of inequality measures, but just to take you through briefly a few that you may want to consider. There's simply the range normalized by the mean utility. You can do that. I use this example just to illustrate mainly that you can linearize that objective function, even though it's a ratio of two variables, of two expressions. There's an old technique by Charnes and Cooper, they were actually at CMU, called linear fractional programming, in which you can linearize a ratio of expressions, of linear expressions. And this is the way it's done here. You can look at this later if you're curious. These slides will be posted on my website. Okay. And as a result, the problem, if it starts out linear, it remains linear. So it's a useful technique for a number of these objective functions I'll be discussing. Relative mean deviation is a similar one. It can be linearized, okay. Coefficient of variation is basically a normalized standard deviation, which is very familiar to people, okay. That can't be linearized. That's nonlinear, but at least it's convex, okay. The best known, of course, is the Gini coefficient, which is used to measure wealth distributions all over the world. And basically, it's the ratio of this blue area to the area of the triangle, where the curve is the Lorentz curve. That's the cumulative wealth distribution. So, the more inequality you have, then the more curved that curve is. Whereas if you have perfect equality, the curve becomes a straight line. Okay, that's the Gini coefficient, very well known. Okay, and it has a linear model that can be linearized. It's very nice for that reason. Okay, something that's related is the Hoover index. It's also actually proportional to the relative mean deviation I showed you a moment ago, and the Hoover index is proportional also to the vertical distance between the diagonal line and the Lorentz curve. It's an interesting fact, and it can be interpreted as the total amount of utility that would have to be redistributed to achieve perfect equality. So it has a very nice interpretation, the Hoover index. Okay, so those are the inequality measures. There's also a very famous measure due to John Rawls, a philosopher, probably the most famous philosopher of the 20th century, okay, or one of them. And this appears in his book, A Theory of Justice. He has something called the difference principle, which says that inequality is justified only to the extent that it increases the utility of the worst off. So that gives rise to a maximizing the minimum, a maximum objective function, which is sometimes used in equity contexts. There's actually a very famous social contract argument for this criterion. Basically, it says, suppose we have a worldwide constitutional convention where we get together and try to design society. And Rawls argues that no rational person could agree to a social arrangement if it would put him on the bottom of society. No one could agree to being on the bottom. The problem here is that we're having to make this agreement before we find out where we're going to end up in society. We don't know whether we're a CEO or a farm laborer before we decide how to design society. So how could anyone agree to a society in which you could end up on the bottom? Only if you would have been even worse off under another social arrangement. Okay, so this is why to have a rational social contract, we have to maximize the worst off, maximum. That's the argument. And this has been discussed in literally hundreds of papers over the years, a very carefully studied criterion. This is how it looks mathematically. It's very simple. You just maximize the minimum. It has a couple of problems, of course, and fairly serious. One is it can call for enormous sacrifice. So here's the contour graph for the minimum. Okay, we're trying to maximize the minimum. And let's suppose this is a medical example. We have two patients in the hospital. Patient one has a mild illness, a flu or something like that. The other patient is seriously ill, or it's very expensive to treat. And the green region is the set of possible utility outcomes given the treatment budget we have, giving our staff resources. Okay, so it's possible to grant a lot more utility to patient one because his illness is not very serious, whereas even if you go all out for patient two, he's still in pretty bad shape. Now, if you maximize the minimum, you pick this point here, the green point. Okay, and notice how much patient one has to sacrifice. So we're actually being asked to bring patient one's suffering down to the level of the cancer victim. Okay, we have to, in order to equalize them and maximize the minimum. Well, that's a very strict, rule, and it may not be appropriate. There's also the issue of, suppose we place bounds, upper bounds on how much resources we can direct to these two patients. Then, for example, in this feasible set, we have upper bounds on both. This green dot on the left is equal from the point of view of social welfare to the one on the right. Okay, even though the one on the right it provides a lot more utility as a total. So that's again a problem with the maximum. Okay, one way around this, we're going to see later, is to use a leximax criterion. That is, you maximize the worst off, then holding that fixed to maximize the second worst off, and so forth. And that way you don't have this issue of wasting utility. Okay, so this is the leximax criterion we'll come back to. You can compute a leximax more or less by sequentially optimizing the first worst off, the second worst off, and so forth. But that's not guaranteed to work if there are ties. So if you have ties for, say, the second and third worst off, then you have to enumerate all the ties, and that could become exponentially complex. Another one is the Macloon index. It's actually fairly commonly used, particularly in the public sector, in education, and so forth. And basically, it measures how badly people are off on the bottom, the lower half. So it's proportional to how disadvantaged the people are who are below the median. Okay, so basically, it compares the total utility of those below the median to the utility that would result if they were all equal to the median. Okay. So it's a bit hard to formulate. It's a nonlinear integer programming model. It can be linearized using the Charnes-Cooper technique I showed you. So you get a mixed integer programming model. But this is the most difficult one, the model we've seen so far. Okay. Now you could also take convex combinations of utility and fairness. It seems like a obvious multi-criteria optimization way to do it. The problem here is you don't know how to weight the two. So for example, you can take a convex combination of total utility and Gini coefficient. The problem here is that utility is measured in some units, like quality adjusted life years, and Gini is dimensionless. So you're trying to combine two quantities with different dimensions. And what does the multiplier lambda mean? I have no idea what it means. So we don't know how to adjust the multiplier in these convex combinations. That's a problem in general with this type of combination. Okay, so for that reason, people have proposed other approaches. One very well known, that's been used in engineering for a long time, is alpha fairness. Okay, so here the social welfare function is parameterized by alpha, And when alpha is 0, you get a purely utilitarian. When alpha goes to infinity, you get maxim in. And when alpha is in between, you get something in between that balances utility and equity in an interesting way. Okay, so it's a nice function. Where does it come from? Basically, it's just the integral of a power law. It's the integral of power law. So engineers tend to think in terms of power laws because very often nature works that way. So here we just take an integral of that and you get this criterion for a social welfare function. And it also can be interpreted as specifying a certain trade-off rate between two players. Okay, so it's an interesting one. It's nonlinear. It's irreducibly nonlinear, unfortunately. But since we're maximizing a concave function, it's not too bad. So you may want to consider using this subjective function for an appropriate alpha in your model. It's very often used. Okay. Again, we have a problem is, exactly how do you choose this alpha, How do you know the alpha is the right value for your application? Well, it's hard to say. So there we have another issue. Also, it turns out that under this criterion, an egalitarian distribution can have the same social welfare as a distribution with infinite inequality. So here's a little example, assigning utilities 1, 1 to two players has the same social welfare as this assignment in which one of the player has infinite utility. That's sort of a queer outcome of this criterion. Okay, a special case, a very famous special case of alpha fairness arises when you set alpha equals 1. This gives you the Nash bargaining solution. Okay, this is not the Nash equilibrium you've heard about in game theory. This is very different. This was actually Nash's first paper. Before he wrote his paper on the Nash equilibrium, he got the Nobel Prize, he wrote this paper on the Nash bargaining solution. I think it was 1950, yeah, 1950. Brilliant paper, absolutely brilliant paper, which he gave an axiomatic justification for this criterion. For alpha equal 1, it can be expressed in terms of logarithms as well as product. Okay. So some advantages of this is, well, it has a very nice geometric interpretation I'm going to show you. And as I mentioned, it does have theoretical justifications and is widely used, particularly in telecom. So this is what you do. Here you have two players, okay? The D here is the starting point of the bargaining. This is what people enjoy in way of utility before they start bargaining. And U is what they end up with, okay? And the yellow region is the feasible set possible utilities. So we want to adjust the U to maximize the area of that rectangle. And that's the Nash bargaining solution. Isn't that cool? Okay, so it's very nice. Now, there is a problem with this solution. There's always problems, right? And the problem is this. Let's suppose that this region under this line here, this crooked line, I think that's a green line, I'm not sure, maybe it's a black line. Suppose that's the feasible set under there, okay? And we're going to increase the size of the feasible set like that. So the Nash solution moves from the dot in the middle to this dot over here, okay? You notice that player 2's utility allotment actually goes down when the feasible set increases. So it's been argued that this is irrational, right? If you have more possibilities, then no one should be worse off than before. But in this case, one player is worse off than before. That doesn't seem rational to some people. Okay, so this gave rise to an alternative called the Kelly-Smordinsky bargaining solution. So both of these solutions can be seen as the outcome of certain bargaining procedures, which I won't go into now. Okay, so this is how it works. What you do is you consider the ideal outcome. That is, you say you look at player 1 and see what the maximum utility that player could have is if he gets all the resources. Then you do the same for player 2, and you plot that point as the ideal solution. Now you draw a line to the origin, and this intersection with the boundary of the feasible set is the Kelly-Smordinsky solution. Okay? So it doesn't have this problem I mentioned before. If you increase the size of the feasible set, then both players are going to be better off. Okay, so you have this monotonicity property that you want. Okay. So this has been proposed primarily for situations like wage negotiation, price negotiation. And basically what it does is to maximize each player's fraction of his total potential, right? You maximize each player's fraction of their potential utility on the condition that that ratio is the same for all the players. So each player gets the same fraction of his or her maximum potential. So this seems reasonable, for example, like you're negotiating a contract with your company, a union contract. Each player gets this, gets 80% of what it could have if it got everything. Maybe that's fair in some sense. All right, so that's the Kalai-Smardinski solution. And well, it has a few problems. It's not always appropriate. For example, in medical context, suppose you have a patient who's very ill, has cancer, and another patient who just has, the sniffles. Okay, are you going to require, the patient with the sniffles to have the patient with one to have only the same fraction of his total utility as the other? Maybe you should give the cancer patient everything they can have, right? And not worry too much whether the guy with the sniffles gets a cure. Okay, but that would violate Kalai-Smardinski because each player should have the same fraction of his maximum potential. Okay, so those are some of the criteria that have been suggested for compromising between equity and utility. Now, the field of AI has also gone deeply into this fairness issue. And as you may know, there's been an explosion of literature on AI and fairness, hundreds of papers. And there's, 2 or 3, 4 conferences that deal specifically with this issue. Yeah, and most of this literature deals with statistical fairness metrics. That is to say, you have 2 groups. You want to make sure you're fair to a minority group as opposed to the majority group. Fair treatment. So that's been the preoccupation of this literature. So let me give you a brief review of what people are doing in this area. Okay, so it's based on statistical measures of classification error, classical measures from statistics that go back maybe even a century. Okay, so it's an old ideas in a way. And you might apply this, for example, to a mortgage loan application. So you have people applying for a mortgage loan. They have a vector of characteristics, their income, their credit rating, and so forth and so on. And you use some kind of machine learning, neural network or whatever, to predict whether this person is going to repay the mortgage loan. And then you award the loan on that basis. Okay, that's how it works. Now, it turns out that people who come from, say, low-income neighborhoods sometimes don't get the mortgage loan simply because they come from that neighborhood. Okay, because statistically, people from that neighborhood don't repay their loans. Now, maybe, this particular applicant is in good financial shape, but because of the correlation in the statistics, you don't get the loan. And this is particularly a racial problem because it's probably, a minority race is the primary population of the neighborhood. So you get racial discrimination. Now you can take all the racial variables out of the data if you want, but still it's latent. These correlations are latent in the data. So you have unfair outcomes. So people are discriminated against because of their race, even though their financial characteristics are like anyone else's. This can happen. So we want to be able to detect this and correct for it. Okay. So here's what we do. Rather than having a vector of utilities that we used before, those utilities become yes/no decisions. So each party concerned, we don't measure his actual utility outcome. We just measure whether that person gets a loan or not. So we have a 0-1 vector, actually 1 - 1 in this literature. Okay. All right. So what's the rationale for doing this? Well, because it's, for one thing, it's often the law. In many countries have affirmative action laws and quotas and such things. You have to be fair. Also, it just sort of appeals to common sense. There's a widely shared intuition. We should be fair in this sense. Okay, even though it's not very well defined what fairness means here. Okay, so some of these metrics are based on true positive, false positive, and so forth, like in statistics. And I'll show you 3 or 4 of them. Certainly the primary objective here is to maximize the accuracy of our prediction. We want to predict who's actually going to repay the loan, for example. But for checking equality, we compare the minority group with the majority group and see how many of those guys got the loan. So if it's the same proportion gets the loan, do we have demographic parity? That's the simplest form. The problem here is that suppose the minority groups is actually more qualified than the majority group to get a loan. And then you're going to force them to get the same probability of being awarded a loan, which perhaps is a discrimination against them. Okay, so demographic parity is, is problematic for that reason. Something called equalized odds takes into account the number of people in a group who are actually qualified. Okay, so the same fraction of qualified people will get a loan. Okay, perhaps that's more appropriate. That's called equalized odds. Also, the accuracy of the prediction, accuracy parity is a very similar one, could be used. Okay, predictive rate parity looks at the fraction of individuals who are selected that should have been selected. Okay, for a loan, for example. This sort of measure is also used, say, for college admissions or for parole decisions, where it's very controversial because it's non-transparent. The machine says you don't get parole, but it doesn't say exactly why. It just gets in the statistics somewhere. So it's very controversial. And there's something called counterfactual fairness, which I won't try to describe very much here. It's too complicated, but it uses Bayesian network, causal networks, to try to tease out what would have happened if you had been a different race when you got your loan decision. Okay, would it have been the same if your race had been different? So it's a counterfactual type of test. Okay, we don't have a good mathematical model for that one. These other guys have mathematical models. The problem with predictive rate parity is it's very difficult to solve. Highly nonlinear, non-convex. The others are fairly easy. They're convex models. Okay, so this is what people are doing in statistics. There are some problems here. One is you're not really.
Can I ask a question? There's a question from
Yes.
the audience, maybe regarding the mortgage loan example.
Yes.
What would push or motivate the banks to reform their loan policies to be more equitable?
Well, for one thing, it may be a legal requirement. People can bring suit under discrimination laws in several countries, like the US. So that's one motive. That's the main motivation, actually. And also public relations, image, and so forth. They want to put forward an image of being fair, okay, and avoiding complaints from their customers. Okay. And I have being in business ethics, I have to grant that many business people just want to do the right thing. Okay, they want to be ethical. Okay. Okay, so so one problem is that we're not actually measuring the level of utility that results from our decision. We're just measuring the yes/no decisions and comparing those. So it's a limited perspective. And then which of these fairness metrics are we going to use? Equalized odds, demographic parity. There's actually about 70 of these that have been used, in the literature. Wow, which one? No one really knows. How do we decide? There's no principled way to balance equity and efficiency in these decisions. We want accuracy, but we also want fairness. Okay, it's good to predict accurately who's going to repay because that maximizes utility, right? It's disutilitarian for people to default on their loan. It's a disaster. Okay? And finally, which groups are we going to consider as protected groups? Which minorities are we going to consider? Maybe female, African American, immigrants. Which ones count? Now, there's some legal constraints here, but apart from that, we don't really know which ones ought to be considered. It's a deep problem in the philosophy of ethics. Okay. Now, let me take you through some models that combine utility and max-min. Okay, and I'll begin with a proposal by these two people. And they might be called threshold approaches, threshold functions. So basically what we're doing here is that we're going to try to be fair. Okay, we're going to maximize the worst off, for example, Rawlsian criteria, but not to the point that we sacrifice too much efficiency. We don't want to go too far with this. Okay, so that's one approach. The other approach is an equity threshold approach, where we start out maximizing utility, but not to the point that we become too unfair, right? So our first impulse is to maximize utility, but not to the extreme where we disadvantage people. That would apply, for example, to the power restoration problem. We want to get the power back as fast as possible, but not to the point that we disadvantage the rural customers too much. Okay, that would be an equity threshold. Okay, so we have those two kinds of thresholds. So utility thresholds, where we start with fairness, but we don't become too costly with respect to utility. And you can draw a two-person function like this. So what we're going to do, this is the Williams and Cookson approach, is to say that when the utility difference between the two players exceeds some threshold delta, then we're going to treat it as a utilitarian problem. And if it does not exceed that threshold, we're going to treat it as a max-min problem. So you get these contours. Now this line here represents the feasible set. So this point here is the max-min solution. This is the fair solution, but it causes one player, player one, to sacrifice, it causes player two to sacrifice a great deal below what he or she could have in order to benefit player one. Player one is very hard to benefit at this point. It's very expensive, to benefit this player because of the steepness of this line. So it turns out in this case that for this particular value of delta, we have a greater social welfare by awarding utilities as shown by this dark line here. If I get my cursor back right here, rather than max-min. So we go to utilitarian solution in that case. Okay, so that's the proposal. This is the opposite. This is the equity threshold proposal here. So this would be the optimal solution for equity threshold, okay? The purely utilitarian solution is up here, but it really deprives player one of a great deal, right? Player one's in really bad shape here. So perhaps in this case, we don't want to go that far with utilitarian. So we use the black dot, which is somewhat kinder to player one. All right. So the utility threshold, the first one I showed you is better usually for medical applications, where fairness is really a sensitive issue, and in politically sensitive context, where people are really worried about fairness. Whereas the equity threshold is usually better in like telecommunications and disaster management, where overall utility or throughput is the major criterion, but you don't want to go to the extreme that you're disadvantaging people too much. Okay, so it has different range of applications. Okay, now what I'm going to do now is to return to this utility threshold with the max-min and generalize it to n-persons. Okay, this is some work I did with Paul Williams. It's not obvious how to generalize it, but you can do it this way. And when you do this, when you use this function, basically you have something called a fair region, right? If you're within delta of the worst off person, then we're going to treat you with priority. We're going to give you priority. Whereas if you're so well off that you're more than delta, better off than the worst person, then we're not going to give you any special priority. That's what this function does. Okay, and then you adjust delta in advance, okay, by deciding how badly off do you have to be to deserve special consideration. Who do we consider to be disadvantaged enough to get special consideration? Okay, so there's some practical interpretation of what this parameter is, unlike the alpha. Okay, so this is maybe an advantage here. And if you pick the delta equals 0, you get utilitarian, purely utilitarian. If you pick delta to infinity, you get max-min. Okay. All right, so the model looks like this. It's a MIP model. It turns out to be sharp. That is to say, the linear relaxation is the convex hull of the feasible set. So it's the best possible MIP model you could have for this problem. Okay, now it has a couple of interesting properties. If you have a simple budget constraint, so this is the only constraint you have in the green region or the feasible utilities, then it turns out that by adjusting the delta, you either get a purely max-min solution as you do here, or you get a purely utilitarian solution as you do here. Okay, it's one or the other. So it's a little bit disappointing in that respect. It's one extreme or the other. You get nothing in between unless you have more complicated constraints in the problem. Okay. Now also there's an interesting fact, a structural fact about this problem. Let's suppose you have this budget constraint, and in addition you have upper bounds on the utilities you allow either player to have. Then it turns out at most one player will have a utility between his upper bound and the minimum utility. At most one, not two. It's never two. It's always just one, even if you have many players. That's a surprising result. And that's the work I did with a student and Peter Zhang. Okay. Now, a problem with this is that we're using max and min as our fairness criterion, and we saw the problems with that. There's a lot of solutions in which are different with respect to equity because we only concern about the worst off. We're not concerned about the second, third, fourth worst off. So all the solutions in this area here, for example, count the same with respect to social welfare, even though they're very different from the perspective of equity. Okay, so this is how you generalize this to in-persons. So the equity threshold can also be generalized to in-persons. Okay, that actually gives you a nice linear programming model. It's a lot easier to deal with. It looks like this, okay, because you have convex contours. Okay, but again, you have this problem that with the max and min, it only cares about the worst off and not the other guys that are badly off. Okay, now the proposal that I'm making here in this talk, okay, goes something like this. So what we're going to do is to combine utility with leximax rather than utility with max and min using this threshold approach. Okay. And so we get a sequence of social welfare functions that look like this. So I won't go through the details. It's actually rather subtle, but we maximize these social welfare functions sequentially. The first one gives us the utility level of the worst off person, and you maximize the second function to get the utility level of the second worst off person. Each time you're maximizing a social welfare function that combines utility and fairness, okay? And what you get then is a solution in which you give the highest priority to the worst off, somewhat less priority to the second worst off, and so forth, up to the individuals that are more than delta above the lowest, and those all get the same priority. They're treated in a utilitarian way. So that's the plan. And as you see, you don't get this region here where everyone's sort of the same social welfare. It differentiates based on the second, third, and fourth worst off. Okay, so it's a more sensitive measure of utility. And here you get much more interesting solutions than you do when you're just using max and min rather than leximax. The model is a bit complicated, but we found you can solve it usually in a few seconds. Okay. All right. And we have some valid inequalities as well. It looks something like that. Tighten the model. It's not a sharp model, but you can tighten it up. So now I want to show you a couple of applications. Fairly realistic. One is inspired by the National Health Service. And this is a model I worked on at LSE with Paul Williams. And what we have here are a group of patients, and they have these diseases and possible treatments. So for example, some of the treatments are pacemakers, hip replacements, aortic valve replacements, heart bypass surgery, heart transplant, kidney transplant, and kidney dialysis. And for each of these, we have the cost of the treatment, the quality adjusted life years that result for the patient with or without the treatment, and the number of patients in each disease category. Some of these diseases have subcategories that vary with the severity of the condition. Okay, so we want to allocate limited treatment budget to these patients, decide how much of each group gets the treatment. That's the issue. Okay, so the model looks like this. I won't go through the details, but here we have continuous variables. So it's no 0-1 variables in this problem. So this is a solution in which we combine utility with max and min. Okay, that's the first threshold model I showed you. And what's going on here? So for each of these treatments, we have a colored bar to indicate whether the patients in that group gets the treatment, depending on the value of the delta. Remember that delta parameter. So basically at the left end, this is a purely utilitarian solution. So if you're just considered it, the total utility, everyone gets pacemaker, everyone gets hip replacement, but nobody gets dialysis. Dialysis is just too expensive, okay, because it's an ongoing treatment rather than one-time surgery. Okay, it's just too expensive. Not enough bang for the buck. So this is what happens with pure utilitarian. And as you go up the other end, you get purely max and min. You're only concerned about the worst off in this group, the worst off patient. And then we transfer resources, as you see, to dialysis because they're worse off. And heart bypass. Actually, heart bypass patients do fairly well without the surgery on the average. Okay, so they're not so badly off as these guys. These guys are going to die without dialysis. Okay. Now, modify the model to combine utility with leximax. So we have a more nuanced measure of utility. And you see how different it is. I'll flip back here, see? We have a lot more action over here at the far left. So the transfer of resources from these heart bypass surgery to dialysis occurs within one QALY. That is to say, patients who are more than one QALY better off than the worst off are going to get dialysis, whereas here they had to be 5 QALYs, 5 quality adjusted life years worse off. You're going to live 5 years less, okay, before they start qualifying for kidney dialysis. So you may say, well, this is much more reasonable here. Well, I think it is reasonable because we're taking into account not just the worst off, but the second worst off and third worst off and so forth, disease. And also you see a lot more subtlety in what's going on here. I won't go through the details. You could spend an hour or so, sort of perusing these results to sort of absorb all the nuances of it. Okay, one more example, and that's disaster preparedness. So this is based on an earthquake shelter problem that was posed in Istanbul. So here we want to build shelters in various potential locations so that when the earthquake hits, the population can go to these shelters and find food and water and so forth, all right? Now the original model was stochastic because you don't know which roads are going to be out when the earthquake hits. So we took out the stochastic element to simplify the problem. So what we have, basically here we're measuring utility by the distance from the nearest shelter, okay? So it's negative utility. And we want to be fair as well as efficient. So this is a solution in which we're combining utility with max-min. Okay, so we only worry about the worst off. So what's going on here? Each of these horizontal lines corresponds to a neighborhood, okay? And this vertical position corresponds to how far they are from the nearest shelter. So these guys at the bottom are very far from the nearest shelter, and these guys are very close at the top. And then on the other axis, we have the delta. So it will become more and more fair as delta increases. And the green here is the fair region. These are the guys who are within delta of the worst off. Okay, so as you see, as the delta increases, well, we have some people here on the bottom who get as much as they can, but they don't increase anymore. This is because these guys, the worst off guys, are very far from all the potential shelter locations. So you can't improve their lot. And because this model only worries about the worst off, once it takes care of the worst off guy, it doesn't really care much what happens up here to the others. Okay, but if you do care, if you have a leximax, then you get a very different pattern. Okay, so as you can see, as delta increases, then a lot of these guys on the bottom start getting closer to the shelter because there's a second worst off, third worst off, and so forth. They're given priority, and they're given more priority as delta increases. And some of the guys at the top have to sacrifice a little, to make way for the guys who are on the bottom, to benefit them. So again, I think you get a much more reasonable, and there's a lot of nuance and little details in this one you look at and interpret, which I won't try to do right now. Okay, so that's my talk. And I have here some references. There's a tutorial I just gave last week at the CP meeting on equity modeling. It goes for an hour and a half, so you can click on this and look at the tutorial. There's also some written references. The second one here is has all the citations that I've mentioned to the literature. Okay, so I guess floor is open for comments or questions.
Absolutely, wonderful, thank you very much. So the audience, if you have any questions, comments, please go ahead. All right, so we have the first one. How does this topic relate to cooperative games?
To cooperative games. Yes. Yeah, okay. Yes. That's not well understood, let me say. We're just seeing people beginning to look at the connections between this type of fairness and game theory. In game theory, there's no simple relationship between cooperative game theory and distributive justice. Okay, it's something that deserves some more research and better understanding. I'm not too clear on it myself, what exactly the connection is. So you may be familiar with the famous prisoner's dilemma, okay, which is a weakness of non-cooperative game theory, right? So you have these solutions in which everyone's worse off because they're an equilibrium solution. Cooperative game theory, you have a core and so forth that tries to avoid this type of thing. To what extent do you avoid prisoner's dilemma so as to achieve some kind of distributive justice? That's an interesting question. I don't have the answer because cooperative game theory is so complicated. You know, it's really has a different approach and a different set of values than distributive justice literature. So yeah, it's a good question, but I can't answer it.
All right, thanks, Professor Francis, for this interesting question. Any other questions or comments, thoughts? Maybe while some of us are typing, let me ask maybe one quick question. So we've seen the advantages of this Lex version of the model, but any potential drawbacks if we consider now all of these first off, second first off, so on and so forth?
Yeah, well, one drawback is you have to solve a sequence of optimization problems. So generally you're solving a sequence of MIP problems. Okay, so it's a computational issue. Now we didn't have a problem, you know, basically for the harder problem here was the shelter location. It would solve in about 10 seconds for each value of delta. That wasn't too bad. But in larger problems, that could become an issue. Also, if you have nonlinear constraints, then you have a discrete nonlinear problem, and that could become a computational challenge. So I think in a case like that, you would want to use a piecewise linear approximation of the nonlinearities, particularly in the utility functions, to make it more tractable. So tractability could be a problem in large instances where you have a lot of nonlinearities. So that's certainly an issue. Also, there are many concepts of fairness, right? There are several distinct concepts of fairness, and they apply to different practical situations. So you have to decide whether this particular concept of fairness, you know, leximax and utility, is appropriate. And there's no well-defined way to do that. And also the way it combines utility and leximax can be questioned. So, you know, I mentioned that those who are nearer the bottom get higher priority. Okay, so how much more priority do they get? Well, the one on the bottom gets priority equal to the number of people that are in the fair region. There's the number of people that are within delta at the bottom. The second lowest gets priority, that's that number minus 1. The third lowest gets that priority equal to that number minus 2. Okay, and then on up to the top. So why do we do it that way? We do it that way because you must do something essentially like this to get continuous contours. Otherwise, you have discontinuous contours. So the continuity of the contours basically dictates the shape of these social welfare functions. It's a mathematical result. You say, okay, well, this is good for mathematics, but is this really what we want in the way of combining fairness and efficiency? Is the mathematically imposed solution really what we want? Well, maybe, maybe not. So I'm not sure. So that could be a weakness. You know, we don't have a foundational justification for this particular mathematical result, a philosophical justification for it.
I see. Thank you. So we have one more interesting question, which was also on my mind actually, from Xiaojian Li. So could you provide some comments about Pareto front on fairness and efficiency?
I missed one of the words, comments about what?
Can you comment on the Pareto front on fairness and efficiency?
Yes, okay. Yes. So are these social welfare, so the socially optimal solutions we get Pareto optimal? Not necessarily. Not necessarily. That's a little surprising. That's actually quite subtle. The reason for this is quite subtle. It took my student and I about a year to figure this out, what's going on. Okay. In practice, it's almost Pareto optimal for example, in the two shelter location problems, in the first one I showed you, it is Pareto optimal. In the second one, there are like 3 or 4 out of 50 utility assignments that are not on the Pareto optimal frontier. So what do we do about that? We just go through and maximize those guys. We just do a utility maximization post-processing, which is very easy to do. It makes slight adjustments in 3 of the 4. Now we get a Pareto optimal solution that looks almost exactly like the social welfare optimum. Okay, but in theory, it doesn't have to be Pareto optimal. Why? The basic reason is when you maximize a sequence of social welfare functions, even if you're concerned only about getting a leximax, a pure leximax, maximizing that sequence, maximizing the worst off, second worst off, third worst off, doesn't guarantee that you'll get a leximax solution. Doesn't guarantee it, because you could have ties and you may resolve the tie the wrong way. So this is what we're doing. We're resolving some ties not quite the right way to get a leximax and therefore to get a Pareto optimal solution. So to be guaranteed a Pareto optimal, you have to go back and resolve all the ties just the right way. Okay, and that's not practical.
Are they potentially weakly non-dominated, if not non-dominated?
Theoretically, yes, but the difference in practice we've found to be very small. And you can always correct for this. You can always get Pareto optimal just by going through and maximizing utility, subject to the ordering of the utilities, the ordering of the individuals. So it's theoretically it's a thorny little problem. In practice, we found it really makes no difference.
So I will take one more quick question. And for those of you who are interested, as our students, please feel free to join our meet and greet session shortly. But one more question. Any work that talks about how to alleviate reverse discrimination?
Reverse discrimination. Okay, so discrimination usually refers to the AI type of fairness model. That is where you're comparing 2 groups for fairness, okay? And there you can have reverse discrimination. And this in fact happens. So this happens, for example, in demographic parity, when you require that 2 groups have the same fraction of benefits, even though one group may be more qualified. And reverse discrimination actually occurs. For example, in Indonesia, there is a quota law that favors the Bumi Putra, that is the indigenous people. And this is seen as reverse discrimination, okay? And it's because they're using essentially demographic parity criteria. So yeah, the extent to which you should use reverse discrimination really is a philosophical issue that society has not resolved. When is it allowable and when is it not allowable to achieve larger social gains? And no one has reached consensus on this issue. So until we reach consensus on the underlying ethical issue, we don't know how to model it. Okay, so we got to decide what to do about this first. Then we'll know how to model it. So I guess that's what I would say there. It's an ethical problem, not a modeling problem.
All right, so with that note, I think we can conclude our seminar today. Thank you very much, everyone, for joining us. And thank you very much, Dr. Hooker, for this wonderful talk and for stimulating ideas. So I'm sure some of us will be definitely checking the references that you provided. And with that, yeah, thank you all again. And Dr. Hooker, so we do have this meet and greet session. Have you received the Zoom link?